I, I want to introduce the last speaker. Regev is with the CTO office of the Essence Group, and he will talk about breath monitoring, remote breath monitoring.
Hey, hi everyone. As mentioned, my name is Regev. I'm very happy to be here talking about this project from a company called the Essence Group. It's a 23-year-old company with over 250 professionals working for it. What we do is looking at the connected home problems and try to solve it. I'm from a department called the CTO's office, and what we try to do is to predict what kind of technologies will give the company revenues in the next few years and try to prototype or research these technologies. What I'm going to talk about today is a simple video-based breathing monitor. And the main idea behind it is basically to track the torso movements through time using the video, and secondly, use this information to estimate the breathing frequency of a subject. The motivation behind it is to be a complementary algorithm, or even a modality, if you will, that can take over when facial video is not available. We all know the motion-based and color-based algorithms for vital signs extraction that really needs a very close-up of the face of the subject. So when that is not available, our algorithm can complement this and basically give some sort of a more reliable, smooth operation of vital signs mechanism. Another thing that it can do is complement another modality, for example, a radar, and I will talk about that later. Possible application for this can be elderly care. We want to monitor our seniors in their homes while they're sleeping, while they're eating, and so on. And also baby monitoring. This is the high-level algorithmic flow. I divided it into three main layers. One is the computer vision layer, in which video frames of, say, 10 frames per second are extracted and streamed. And on top of that, we have the optical flow done on points extracted from the frames. These points are basically fed into a spectral estimator that is used in conjunction with a generalized likelihood ratio test that check adherence to the sinusoidal wave-like breathing model. Next, all the surviving points are then fused into one estimation of the breathing. And this is the fusion part. So basically, there is the computer vision part, and there is the rigorous analysis or spectral analysis part. The optical flow tracking, what we use is the Lucas-Kanade's algorithm. So basically what we want to do is track the variations of point location in the image through time. And the variation is given both in the x-axis and the y-axis. And basically what we got, for example, this is 1 point, variates through time. And we see that we have the sinusoidal wave-like model both in the X and Y, but we also see that it carried on a trend, which is basically a slope in a DC term. Also, we see that the actual points in even the axis can be separated in terms of amplitude or SNR. The assumed model, some notations. So basically what we look at n points, which we call modalities, which we want to fuse all these modalities to a one coherent and perfect estimation. We have the modality index I, we have the sample index K, which is basically a time index. And Ki is the ith modality number of observed sample, which can change from modality to modality. This is the assumed model, or the model that we want to extract our information from. By the way, the PowerPoint is totally corrupted here. So anyway, so we have some parameters that want to estimate. What we want to do is just keep track of the what we call omega b, which is the breathing frequency. The rest are nuisance parameters, and we add some, Gaussian IID noise to that. What we get in reality is a trend on top of the sinusoidal wave. This trend can be characterized by a slope and a DC term, which adds two more parameters for us to estimate. So what we want to do is estimate these parameters and then subtract it from the signal. What we use for this trend removal algorithm is basically the recursive least squares algorithm to estimate a trend line, and then once it's estimated, it's subtracted from the signal, which leaves us with a pure or a little bit noisy sinusoidal wave-like that we can actually extract some spectral information out of. This is the algorithm we see here in the top. The first 5 lines are really the initial conditions for the algorithm. Use the least squares. And then it iterates through a Kalman-like or recursive least squares filter to enhance in each of every iteration the estimated breathing frequency per point, per axis. So once we have estimated this slope and DC term, what we want to do now is estimate the breathing frequency, and we want to do that in real time. We also want the resolution of the breathing estimation to be less than 1 BPM, bits per minute. So if we use, usual Fourier analysis, what we have here is we have to observe the signal for more than 60 seconds, or at least 60 seconds, which leaves us wondering what should we do. So the approach that we took is to use a super resolution spectral estimation algorithm using the well-known Pisarenko method. So in 1973, Pisarenko suggested or observed that the eigenstructure of the covariance or autocorrelation matrix of the data is, it can be used for estimating the frequency. And these guys, So and Chan, in 2004, reformed this algorithm to be iteratively calculated for this case of one sinusoid. We can see here the algorithm. It's very, very simple, actually. It has two main constants that we iterate through calculation. It's A and B. And note that A and B also only rely on the last 3 samples, namely K, K-1, and K-2. These A and B, after each iteration, are plugged into here to calculate the breathing frequency. Moreover, these guys let us have the closed form solution for the variance of the estimator, so we can actually plug this into our fusion algorithm, the maximum likelihood algorithm, to take into account or to, let's say, extract more information or the relevant information from the estimation. We evaluated the algorithm on use cases, actually real use cases, against the Crimera lower bound, which is a lower bound for unbiased estimators. And we see here that this is a snapshot after 10 seconds of video operation. And we see here that as SNR increases, we tend to the bound, and actually we meet the bound, which is the black line here. And what we deal here with is a asymptotically efficient estimator. In order to verify the model, what we used is basically what we want to do is once we have an estimation, first we want to make sure that this estimation falls in the breathing band of frequencies. And this is somewhere between 0.2 to 0.8 hertz. The ones that survive this simple test are going to be adhere to our model, our sinusoidal wave-like model. For this, we developed a generalized likelihood ratio test, which is a simple statistical test differentiating two hypotheses. The null hypothesis being we observed only the noise, and once we reject this hypothesis, so we have our sinusoidal model here. So the model, the actual GLRT is given, in closed form, and is very intuitively understood as a correlation between our observed signal and a sinusoid and a cosinusoid. And this is basically compared against the threshold. The threshold is chosen such that we keep a constant false alarm rate. And it's also given very nicely here. Okay, so now that we have estimated a lot of breathing frequency, and we discarded some breathing frequencies that are not really in the band of the breathing, and we discarded some breathing frequencies that didn't adhere to our model using the GLRT test, we go and we take all these frequencies and we want to fuse them to one accurate estimation of the breathing. So the fusion algorithm is basically uses a maximum likelihood framework. And basically we assume this following model. We have n basically measurements or estimators of the breathing frequency, and we assume that it is carried, the true value of the breathing frequency is corrupted by noise. It can be non-stationary noise, which will be accounted as in the fusion algorithm. And the fusion algorithm is basically solving a weighted least squares problem to this matrix vector equation that we did here. R being the covariance matrix, which is a diagonal matrix of the corresponding variances, and the estimation is given in closed form using the weighted least squares. So we have done some experiments, and we have done actually a lot more. But when I wrote this presentation, we have done it on 5 subjects: 2 babies and 3 adults, using a simple RGB camera and also an IR camera in night. The true breathing rate was counted manually from the video, and also was compared against a radar reading. I will talk about that later. We got a very, very nice results. We got a maximum error that varies from 0.7 to 1 bits per minute after 10 seconds of video. So the maximum being 1 bit per minute, so we meet our determined constraints. However, I have to mention that the algorithm failed in the good features to track step when the subject was not wearing a patterned shirt. But keep in mind that this algorithm is just complementing other modalities or algorithms that are also taken into account for the system that we built. So some results, we see here these 5 subjects. It's 2 babies, a half-year-old and a 2-year-old baby, female and male respectively, and 3 adult males. This one is me, and also 2 males, 30 and 50 years old. And we see the errors using our iterative algorithm. And we see the errors that we get using a total maximum likelihood optimal algorithm, which is really based on two minutes of recording a video. So we see here that the maximum deviation between the optimal algorithm is 0.4 BPM, or 0.5 here, sorry. I want to show you how it works. So I have some examples here. This is me in the winter. This is the points that the algorithm extracted. And once I hit the play button, we see, okay, does it work? Okay, so we see here all the points. We see here all the points that are fused into a one final bits per minute estimate. And in the beginning, it's a little bit jittery, but it reaches a steady state very fast after just a few seconds, and then it just track your breathing very, very accurately. Another example is my colleague. This is done on my colleague, which is here somewhere in the audience. We can see that the algorithm finds a lot of points in other places. Once I play this, you see that the points are moving. And very fast, we can see a reading of the breathing. We can see the jittery transient of the filter, of the estimation filter. And finally, it converges to a final, very accurate measurement of the breathing. Something about future work, and then we go to the happy hour. So what we look at is multiple modalities for the problem of vital signs extraction, or remote vital signs extraction. And one of the modalities that we are working with is sensor fusion of this modality, the camera with a radar. So a radar is actually a very nice tool for this, to track these kind of minute movements of the body. And we've done some experimenting on the feasibility of fusing, and we can see here on this graph there is a almost perfect correlation between the radar reading, which is the blue line, and the video out of this algorithm, which is the black line. So for future work, we want to make a reliable apparatus, if you will, that can track 24/7 a subject breathing and also the heart rate. And we are not yet there, but we are getting there. Thank you very much.
Questions?
Did you have videos with some global motion, like you are sitting but you move the whole body?
Yeah, we did some experimenting with that. It varies. The optical flow will track this motion, and this motion can be subtracted from the the harmonic motion. But if the motion is very abrupt, like someone is flipping over, the whole algorithm should be reinitiated. Thank you.